what I would like to talk about today, oh, I just noticed the bouncy slide thingy over there. It's probably been in front of me for hours at this point. What I would like to talk about today is resistor combination techniques. I'm sorry, what was that? Okay. I'm notoriously unobservant, so it wouldn't surprise me if that thing had been there for 3 days and I just now noticed it.
I think in part of our lab, you running through the output before.
No. So largely, this should be a review of stuff that you learned in your 120 series. We're just going to kind of formally explain why things work the way they work, and then I'm going to give you some tips and tricks and all that kind of jazz. We might look at a problem or two from your web work, and then I'll let you guys get into the lab and the in-class assignment. Okay. So let's first start by formally describing how resistors combine in series. So let's say that we have part of a circuit that contains multiple resistors in series. Let's call this first resistor R1, this second resistor R sub 2, and we are going to have an arbitrary number of resistors in series, so let's call this R sub n, like so. Because this network of series connected resistors is part of some greater circuit, we should expect to see that there will be some total voltage drop across all of the resistors V, because again, a voltage is nothing more than the potential difference between 2 points in a circuit. And my 2 points that I've defined here are the terminals of this series resistor network. And because we're part of a greater network, we should probably also expect to see some current flowing through our resistors as well. Okay. So for the intents and purposes of this derivation, we are looking at what is effectively a single loop circuit where we're representing everything to the left by that known voltage. Okay. So I'm going to define my voltage drops across individual resistors such that the current I is flowing into the positive polarity terminal of each resistor like so. And then I'm going to apply Kirchhoff's voltage law. So this would look like negative V plus VR1 plus VR2 plus any other voltage drops we see all the way out to our nth resistor is equal to 0. And then I'm simply going to move that individual voltage V to the other side of the equal sign so that that voltage V is equal to the sum of the drops over all of the resistors. Now I'm going to use Ohm's law and express all of those resistor voltage drops in terms of that current I that's flowing through all of those series resistors. So that's going to look like I times R1 plus I times R2 all the way out to I times Rn. And I can pretty easily factor out I such that I'll just have I times R1 plus R2 all the way out to R sub n. Now recall from the original look at Ohm's law that we looked at, the equivalent resistance of a network or anything like that is simply the ratio of the voltage across the terminals of the network divided by the current flowing into the network. So in this case, our equivalent resistance, Req, is just going to be the ratio of that voltage V to that current I which is simply the sum of resistor R1 plus R2 all the way out to R sub n. So effectively, whenever we have resistors in series, we just add the values together and treat it like a single equivalent resistance. In a more formal mathematic notation, I'm going to say that Req sub S, representing in series, is equal to the sum from I is equal to 1 to N of R sub K, meaning that we just add up all the resistors that we see in series, and that's the equivalent resistance. Again, something that you guys should already know, but we've formally explained why that works using Kirchhoff's voltage law and Ohm's law. Walker. So the V that we're talking about is this V right here, and I'm performing Kirchhoff's voltage law around this path following that blue line, starting from the bottom left-hand corner and going clockwise. So I get negative V out front because I see the negative polarity terminal first. And then positive all of the other terms because I see the positive polarity terminal first as I follow that path. Okay. All right, so I feel pretty strongly that it's not really necessary to give you guys an example of resistors in series. If you want one, I can happily draw something simple, but this is fairly straightforward. So if you're okay with it, I'd like to move on to resistors in parallel. All right. So for resistors in parallel, we're going to take a very similar approach. We are going to have a network that is part of some larger circuit. And now we are going to have several resistors connected in parallel instead of several resistors connected in series. So I'm going to call this first resistor R1, the second resistor R2, and this can be any number of resistors in parallel, so I'm just going to stretch this out once again to an arbitrary number, R sub n, like so. Because we're part of a larger circuit, it seems reasonable that there will be some voltage drop across this parallel combination of resistors. Additionally, there may be some current flowing into this parallel combination of resistors. And now I'm going to define all of my resistor currents in such a way that I'll wind up getting a positive sign. So because the positive polarity terminal is on top, I want my resistor currents flowing into that positive polarity terminal. So I'm going to have resistor current IR1 like this, a resistor current IR2 like so, and a resistor current IRN like so. I'm just setting up my directions to satisfy the passive sign convention, much like I set up my polarities to satisfy the passive sign convention when we had things in series. So if I apply Kirchhoff's current law, formulation number 1, currents flowing into this network or this top node here equal the currents flowing out, what I will get is a current I, that's the one flowing in, will be equal to IR1 plus IR2 all the way out IRN, like so. Current flowing in equals current flowing out applied at the top node. Now, once again, I'm going to use Ohm's law to express all of my resistor currents in terms of the common voltage V. Because all of these resistors are in parallel, they have the same exact voltage drop over them, which I've labeled as that voltage V. And so what we'll get is that I is equal to V divided by R1 plus V divided by R2 all the way out to V divided by R sub n. And since there's a common factor of V, I can just take that out, leaving me behind I is equal to V times the sum of all of the reciprocals of the resistances. So, according to Ohm's law, the equivalent resistance of this network is once again just going to be the ratio of V to I. And so that's going to look like 1 over the sum of the reciprocals of all of those resistances. Or in a more formal mathematic notation, we can say that for resistors in parallel, we have 1 over the sum from I is equal to 1 to n of 1 over R sub k. All right, so here are our formal definitions for how we are going to combine resistors in series and resistors in parallel. Now, depending on who you had for your engineering 120 class and all that kind of good stuff, you may have been introduced to a slightly different way to combine resistors. So I'm going to introduce that here really quickly. I do want to point out, though, that it works for exactly 2 resistors, and that's it. Although we can expand on that a little bit, okay? So let me explain what I mean here. Let's say that I have a network that contains exactly 2 resistors connected in parallel. So let's call this R1. Let's call this R2. Just to get you guys used to the notation, what I'm trying to find here is the equivalent resistance seen between terminals A and B. Okay. So if I use the relationship that we just derived, what I should observe is that RAB is going to be 1 over R1 plus 1 over R2. Okay. What I'm going to do now is have some fun with fractions. Okay. So I'm going to multiply that 1 over R1 term by a factor of R2 over R2. I'm going to multiply that 1 over R2 term by a factor of R1 over R1. Okay, so I'm just multiplying by fancy versions of the number 1. And what's going to happen is that now I have a common denominator in my denominator. So what I should have is 1 divided by R1 plus R2 divided by R1 times R2. And because of how dividing by fractions works, 1 over that fraction is the same as 1 times the reciprocal of that fraction, giving me R1 times R2 over R1 plus R2. So this is a shorthand notation for combining exactly 2 resistors in parallel, where you don't have to worry about a bunch of wonky fractions and all this kind of stuff, right? You can do it very quickly. So if I have, let's say, a 3 ohm resistor in parallel with a 6 ohm resistor, Instead of saying it's 1/1/6 plus 1/3, I could instead say it's 18/9 or 2 very, very quickly. Okay. This trick here only works when combining two resistors, okay? It should be fairly obvious why it won't work for more resistors if we just look at the units, right? So if we had 3 resistors in parallel and we tried to apply this, we'd have resistance times resistance times resistance, so ohms cubed, divided by resistance plus resistance plus resistance, or ohms. We get units of ohms squared, which is not the correct unit for resistance, right? So this only works when we have 2 resistors. Now, what we could do, let's do it with a numerical example here, okay? So let's say that we have trying to think of something off the top of my head where the numbers will work out reasonably pretty. 12, eight, and 6. So what I could do is I could combine any 2 of those resistors into a single equivalent resistance, and then take that equivalent resistance and combine it with the other resistance using that equation that only works for 2 things. So let's start by combining the 12 and the 8, right? So 12 times 8 over 12 plus 8. 24 over 5. So let's just leave it as that, okay? So this is going to look like 24/5 of an ohm in parallel with 6 ohms. Now we could take that answer, multiply it by 6, and divide by that answer plus 6. So x plus 6, excuse me, x times 6 over x plus 6 winds up looking like a single resistance having a value of 8/3 of an ohm. So if we don't want to bother with the long 1 over the sum of the reciprocals, we can just apply that 2 resistor trick over and over and over again to shrink it down. But I'm lazy enough to where I want to do exactly 1 calculation. So if I have 2 resistors, I use this method. If I have any more than 2 resistors, I use this method because I just don't want to keep doing the same boring thing over and over again. All right, so before we move along to more rigorous examples, does anybody have any questions about series and parallel resistance? Okay. So what I'm going to do here is I'm just going to pop onto WebWork and look at a problem that you guys typically struggle-ish with. Let's look at homework set number 3. Let's look at things here. This is one that you guys struggle with, but it has nothing to do with resistor combination, so we'll talk about that later probably. Let's look at this guy here. So this is a fairly ugly looking network of resistances. And to me at least, it's not intuitively obvious what the equivalent resistance is going to look like between any particular set of terminals. So this will be a good problem to work where I can show you how I deal with complicated resistor networks, okay? So let me draw this really quickly. Diagonals going across like that. So I believe this is terminal A, B, C. Nope, CBA. Not that it matters, but D down here. And let's just make up resistor values. So this will be 60, 30, 10, 25, 100, 50, 75, 40, and 90. So in the homework problem, you are asked to find the resistance seen between selected terminal pairs, right? So we're looking to find the resistance between terminal pair AB, terminal pair AD, and terminal pair BD. So Jacob, pick one of those two, or excuse me, one of those three terminal pairs for us to work with here. So AB, AD, or BD? AD, okay. So our goal here is to find the resistance between terminals A and D. So I grew up watching a show called Pee-wee's Playhouse because I'm old. And as part of Pee-wee's Playhouse, they played a game called Connect the Dots. And that's exactly what we're going to do, except we're going to play Connect the Dots with resistors. Okay. So I'm going to put terminal A way over here on the left-hand side of the page. And I'm going to put terminal D way over here on the right-hand side of the page. And we are just going to form pathways between those two node points. Before we start doing that though, I like to label and identify all of my nodes so I can see where those connections are happening. So this red node here is going to be node C because it's already connected to terminal C. This blue node here is going to be node B because it's already connected to terminal B. This green node here will be node A because it's already connected to terminal A. This pink node here will be node D because it's already connected to terminal D. And it looks like I have two more nodes which don't currently have labels. So we'll call this one on the bottom left E, and we'll call this one on the bottom right F. Realistically, we could, but I'm trying to prove a point here, so I'm not going to. Yeah, so we can pretty easily observe that the 30 and the 10 are in series and the 90 and the 40 are in series. You're 100% correct there. But all right, so I'm trying to find the different ways that I can go from A to D here. Okay, so I look for the easiest pathways first. And to me, the easiest path to go from A to D is just directly through that 75 ohm resistor, right? So I'm going to place a 75 ohm resistor directly between terminals A and D. I'm going to put a check mark by this one to let me know I've already used this one in my drawing. Now, the next easiest path, in my opinion, to go from A to D is to go through node F. So I'm going to put node F here in the middle, and I can go from A to F through the 90 ohm resistor. And I can go from F to D through the 40 ohm resistor. And I'm going to put a check mark by both of those. Now, another way that I can go from node A to node D is by going through node B. So I'm going to put B out here. I can go from A to B through the 100 ohm resistor. And then I have lots of choices, right? I can go from B directly to D through the 50 ohm resistor. So I took care of this guy and this guy. I can go from B to C to D. So let's put C here in the middle. So to go from B to C is the 60 ohm resistor. To go from C directly to D is the 25 ohm resistor. But I could also go from C, so let's take care of the 60 and the 25. I could also go from C to E to D. So I have another little path down here. So here's where E is going to be. So I can go from C to E, which is the 30. And then from E to D, which is the 10. It's zoomed in a little bit for whatever reason. And so now I have a network, and I'm just going to work my way from the bottom up to the top. Okay. So as Christina noticed earlier, we can see that the 30 and the 10 are in series because they have that single node point shared between them, E. So what's 30 in series with 10 look like? 40, okay? So between nodes C and D, I'm going to replace this 30 in series with 10. And I'm just going to put, sorry about that. A 40 ohm resistor. Well, now I can see that that 40 ohm equivalent resistance is in parallel with that 25 because they're both between terminal C and D, right? So 40 in parallel with 25 is going to look like 40 times 25 over 40 plus 25. That I want it to do a fraction because that's horrifying. 40 times 25 over 40 plus 25, 200 over 13. So I'm going to erase these guys, replace it with a single 200 over 13 ohm resistance. Now that equivalent resistance is obviously in series with the 60 ohms, so I'll simply add 60. We get 980 over 13. That 980 over 13 is in parallel with the 50. So we'll do answer times 50 over answer plus 50. We get 4,900 over 163. That is in parallel, excuse me, in series with a 100 ohm resistor. So I'll just add 100. So we get 21,200 over 163. And that's as far as we can kind of simplify that bit, right? So now we're going to move up to the one above it. So that one contains a 90 ohm resistor in series with a 40 ohm resistor, which is just going to look like 130. And now we can see that we have three resistances in parallel. So RAB is going to be 1 over 75 ohms plus 1 over 130 ohms plus 1 over 21,200 over 163, which is just going to look like 163 over 21,200 ohms down here. And I got this to be 34.826 ohms. So this is my preferred technique for combining resistor networks that aren't just blatantly obvious how to do it. So I mean, if it's a network that contains like more than 4 resistors, even with my PhD, I'm still going to use this method. Okay. All right. That's probably one of the harder problems on this homework set. I'm not going to work the in-class assignment for you by any stretch of the imagination, but I do want to give you guys a quick hint. So let's see. This is the last. This should be in-class assignment number 3, if I'm not mistaken. So you're asked to find the equivalent resistance of this big ugly network with respect to a couple of different sets of terminals. The first step that I would take if I were you all would be to find the equivalent resistance of this big ugly thing on the right-hand side, because that's going to be part of the equivalent resistance of all of the other things. And so once you break this down into a single REQ, you never have to deal with this big ugly thing again. Okay. So find the equivalent resistance of that path first, and then this becomes much, much easier. If you choose not to do that, this is just a wildly tedious exercise with you doing the same thing over and over again. All right, that's enough out of me for today, unless anybody has any questions. So you've got an hour and 10 minutes to work on this in-class assignment and also wrap up the mini lab.